Welcome to the video lecture on control of particular contaminants. The type of device we select depends on the size of the contaminants, concentration of the particular matters that are present in the flue gas, and its chemical reaction. So how well it reacts with each other, each other particulate matter or with the components of the flue gas. Volumetric flow rate. So it is the volume of flue gas that is emitted from any industrial operation, and the efficiency of removal of these particulate matters and the cost of the equipments. There are different mechanisms for removing these particulate matters from the flue gas. They are gravitational settling, centrifugal impaction, inertial impaction, direct interception, diffusion, and electrostatic precipitation. Based on these mechanisms, one or two mechanisms, devices will be fabricated, and they are classified as gravitational settling chambers, cyclone separators, fabric filters, electrostatic precipitators, and wet collectors. Gravitational settling chambers. Gravitational settling chamber is used to remove larger and abrasive size particle from the gas stream. Usually the size of the particulate matter will be greater than 50 micrometers. So in the gravitational settling chamber, the particulate matter settled by gravity. So the velocity of the flue gas or the gaseous stream is decreased by increasing the area in which the gas has to be flow. So the area has been enlarged. So from the below figure we can see this. The inlet is a small rectangle, and then gradually we are introducing a trapezoidal area where the area is gradually increased, and when it enters into the settling zone, the settling zone is a long rectangle. So the length is L, width is W, and the depth is H. And again, so it converges into a small rectangle. So the transition is done by introducing again a trapezoidal shape between a larger rectangle and the smaller rectangle. So we have two collection hoppers between the settling zone, below the settling zone. The velocity of the settling chamber is between 0.5 to 2.5 meters per second. So when flue gas is entering with such a velocity, the larger size particle will settle down due to its own gravity. So since the particular matters are settling by gravity, so we are using Stokes' law. So where H by Vt is equal to L by Vh. So H is the depth of settling chamber divided by Vt. Vt is the settling velocity in meter per second, and L is the length of the settling chamber divided by Vh. So Vh is the flow velocity. So the horizontal flow velocity of the gas stream. So solving this, we get Vt is equal to G into rho P minus rho D into dP square divided by 18 into mu A square, where G is the gravitational constant, rho P is the density of the particle matter, rho A is the density of the gas stream, dP is the diameter of the particle that can be settled in this velocity. Mu A is the viscosity of the air. So solving this dP will get D is equal to square root of 18 mu H V divided by GL into rho P minus rho A. So horizontal trace can be introduced to reduce the depth of the settling chamber. So if you are introducing more number of settling zones, then the spacing between each other should be between 10 to 30 mm. So cleaning mechanism require. So, so in order to reduce the depth of the settling zone, multiple tray separators are used. So we can see here there are 4 trays. So which is the cross section is given as a tray horizontal line as a tray format. And we see here, so the dots are the particulate matters that has to be removed in this multiple tray separator. And this is the gravity settling chamber. So the gas enters and it passes through these different trays. So these individual trays act as a individual settling chambers, and the clean gas is taken out at the top. So the advantages and disadvantages of this gravity settling chamber are, so they are low cost, low in energy, so there are no moving parts, maintenance is easy and low operating cost, so they are more reliable. There is low pressure drop and device not subjected to abrasion. So the disadvantages are relatively low collection efficiency, so a larger physical size, trays in multiple tray settling chamber may warp. Next we will see cyclone separators. As the name indicates, cyclone separators uses centrifugal force to remove the particulate matter. So these are used as pre-cleaners to remove larger size particles before entering into a final filtration zone. So we can have multiple cyclone by having several cyclone separator operated in parallel. So how this cycling separator works is by using the centrifugal force. In a cyclone separator, dirty flue gas is fed into the chamber. The inside of the chamber creates a spiral vortex. The lighter component of this gas have less inertia, so it is easier for them to be influenced by the vortex and travel up it. On the other side, larger components of the particle matter have more inertia and are not as easily influenced by the vortex. Since larger particles have difficulty following the high-speed spiral motion of the gas and the vortex, the particles hit inside the walls of the container and drop down into the collection hopper. These chambers are shaped like an upside-down cone to promote the collection of these particles at the bottom of the container. The cleaned flue gas escapes out of the top of the chamber. So we can see the cross section of a cyclone separator. So on the right side we can see the yellow colored dots are the flue gas. So we can see the spiral motion of the flue gas. So the flue gas moves in a vortex. So it is like a spring. So the movement is like a spring type. The bottom is a conical portion. So this is the collection chamber where the settled larger size particles are collected at the bottom. And the clean air is sent out. You can see on the top left side image we can see the clean air. So the inlet and the outlet of the clean air both are at the top side, top part of the cyclone separator, and the bottom is the collection portion where we can collect the settled larger size particulate matters. So this image shows the cross section of the cyclone separator. So the arrow mark indicates the movement of the flue gas, thereby the particulate matter. So this you can see near to the center there are more number of smaller diameter particles, and towards the outer section we can see larger diameter particles. So larger diameter particles can't able to move along the circular motion due to its weight, and hence they are settled down, whereas the smaller size particle, so they have, since their mass is very low, so they move up with the gas in the spiral motion and escapes from the cyclone separator. So most cyclones are built to control and remove particle matter that is larger than 10 micrometer in the diameter. These separators are not effective on extremely larger particular matter. For particles around 200 micrometer in size, gravity settling chambers are the better option. Out of all the particle control devices, cyclone separators are among the least expensive. They are often used as a pre-treatment before the flue gas enters more effective pollution control devices. Therefore, cyclone separation can be seen as a rough separator before the flue gas reaches the fine filtration stages. The advantages are they are inexpensive, simple to design and maintain, require less flow area, low to moderate pressure drop, no moving parts, continuous disposal of solid particle. The drawbacks are low collection efficiency, require much headroom, abrasion problem since the flue gas are moving continuously, sensitive to variable dust loading and flow rates. So we can see a parallel of cyclones. So cyclones are arranged one after the another in parallel fashion. So it is called as multi-cyclone in order to increase the efficiency of removal. So according to Lappel, the removal efficiency is given as dPc. So this is the diameter of the particle that can be removed, which is equal to square root of 9 mu g bc divided by 2 pi ne vi into rho p minus rho g. Bc is the inlet width of the cyclone chamber, and vi is the gas inlet velocity. Ne is the effective number of turns a gas makes in traversing the cyclone. So it is around 5 to 10 in most cases. The pressure drop is given as delta P is equal to K into rho g Vi square Hc Bc divided by 2 into dE square. So K is the constant which averages between 30. So these are the cyclones that are connected in series. Next we will see fabric filters. So they are otherwise called as baghouse or fabric dust collectors. These are designed to use fabric filter tubes, envelopes or cartridges to capture or separate dust and other particulate matter. Their application range from small household workplaces to larger industrial facilities such as coal-fired power plants and cement plants. So you can see, so these are the filter bags. So these filter bags can be of any material. So these filter by means of adsorption technique. So dirty air is passed through the chamber, and this filter chamber consists of a series of arranged filter bags. So the dust particles is adsorbed on the surface of these filter bags, and the clean air is passed at the top of the collection unit. Baghouse consists of filter media or bags suspended inside a casing. Fans on the outside of the housing blow the dirty or polluted air through the filters, capturing the suspended particle matter and solids on the bags and pushing clean air outside. While filtering, a baghouse allows the formation of layer of particle matter on its surface called a dust cake. This dust cake continues to build until the thickness reaches a level Where flow is sufficiently restricted, at this point the bags are clean. Cleaning can be done during operation or offline depending on the type of the bag house. Air is filtered through the bag house. The dust cake on the bag filters continuously thickens. For most bag fabrics, the cake is what does most of the filtering of the particle matter in the air stream. The thicker the dust cake, collection efficiency is increased and the pressure drop as the pathway through the bag become finer and also more restrictive. Cleaning mechanism must find the right balance for this trade-off. Too thorough or frequent cleaning results in a lower collection efficiency and possibly reduces bag life. But insufficient cleaning will cause excessive energy requirements for blower fans. The advantages are they are versatile and flexible for many applications, extremely high collection efficiency for smaller size particles, cost effective when properly designed and maintained, can collect other pollutant with certain fabric coating addictions. Their disadvantages are not well suited for very high dust loads, require a lot of maintenance, limited by high temperature and corrosive chemicals, potential for fire explosions. How can these bag houses can be cleaned? So based on this, we have different types of bag houses. First we will see reverse air bag houses. Reverse air use continuous stream of low pressure air to remove the collected solids. Bags are cleaned by backwashing within a chamber after shutting off the dirty gas flow. That is, the inlet of the dirty or polluted gas is closed and a fresh gas is passed inside with under pressure, so that removes or loosens the dust cake that is formed on the outer surface of the fabric material. The recommended air to cloth ratio for these bags is between 1.7.5:1 and 2.5:1. Advantages are they are typically compartmentalized, allowing sections to be cleaned without shutting off the whole system. Cleaning action is very gentle, with which lengthens the life of the bags. Preferred for high temperature due to gentle cleaning action. Disadvantages are the cleaning air must be filtered, provides no effective means of removing residual dust buildup. Next, shaker bag houses. These bag houses uses mechanical shaking or vibrating to dislodge the dust cake. Bag bottoms are secured to the plate and their top are connected to the horizontal beams. These beams, driven manually or by motor, vibrate to produce waves in the bags which shake off the particle matter. The recommended air to cloth ratio for these bag houses is between 2:1 and 2.5:1. So we can see the cross section of the bag house here. Advantages: so the design and operation are simple, can be compartmentalized to allow section to be clean without shutting off the whole system. Disadvantage: cannot operate in high temperature, more energy and time intensive than the other cleaning methods. Next we have pulse jet type of bag houses. This uses compressed stream to high pressure air to remove particulate matter. During cleaning, brief pulses of air are pushed through the bag, dislodging solids which collect in a hopper below. The recommended air to cloth ratio of these bag houses is between 3.25:1 and 4:1. The advantages are they allow cleaning mechanism to be cleaned while the system is online, more complete cleaning than shaker or reverse air bag houses. It lengthens the life of the bag, operates at low pressure drops and with lower space requirement. Disadvantages are it requires the use of dry compressed air, requires special fabric for higher temperature, cannot tolerate high moisture level or humidity in the exhaust gases. So the cleaning sequence may be intermittent, that is at particular interval, or it may be continuous offline. So offline means the cleaning removal of particle matters is completely shut off and then cleaning is taken. Once it is clean, then it is again open for removing of particle matters. And continuous online is, so once the removal of particle matters and as well as the dust cake removal is taken place. The common filter media used are cotton, vinyl, wool, nylon, orlon, dacron, and glasses. So these have different characteristics against acid and alkali. So depending on the type of the gaseous contaminant present in the dirty gas or the polluted gas, the type of fabric may be chosen. The design key parameters or airflow pressure, that is vacuum pressure generated by the fan, is not sufficient to overcome the static pressure. The filters, several problems will arise. The system will suffer a loss of suction at the collection point. Air velocity. If the air velocity is high, then it creates a hole in the dust bag due to abrasion. If the air velocity is low, it causes dust buildup within the duct and lead to poor dust capture at the inlets. So we have to choose such a velocity that so it is optimum inside the bag houses. Then add to cloth ratio. For bag house to capture the dust from the air stream, the unit must have sufficient number of filters. As the air is pushed through the same amount of filter material, the collection efficiency goes down. So maintaining an adequate air to cloth enables the bag house to operate at peak efficiency, collecting more than 99.9% dust particle that passes through it. So the design procedure is we have to find the minimum velocity of air that has to be passed through the chamber and identifying primary and secondary source of air. Calculate volume of air required and create a layout and size of each section and then calculate the pressure. So these are some of the pictures of shaker mechanism. We can see the bottom portion is fixed and the top portion of the bag house is spayed so that a vibration is created and all the dust cakes can be loosened and it can be collected at the bottom. So this is reverse air bag house where clean air is used gently for cleaning the bags. And this is pulse jet bag houses. Thank you.